Hello, students. Welcome back. We're going to be doing linear and nonlinear system of equations. Right. So let's get started. So up to this point in this videos, we have mostly dealt with functions of one variable or single equations of two variables. So x and y, or x squared and y, or y squared and x. So however, in many problems in science and technology, business and engineering, there are going to be more than one variable. Right, so we're going to be introducing a system of equations, right? Because we're going to have multiple variables which are related to each other, right? And we would want to find a solution to such system. So let's go ahead and start with an example. So when we have two lines, right, two linear equations, we know that at some point those lines can intersect, right? Let's say we assume that it's not a parallel line, then we know that at some point they're going to be intersecting. So that intersection is our solution, right, to the system. So let's take a look at a first example. So example 1, let's say that we have 2x plus y equal to 5. That's our first equation, right? And then we have 3x minus 2y is equal to 4. Okay, so here is an example of system of equations. So that's how we write it down, and then we will put a bracket here. So that means we have two equations, right? This is equation number 1, and this is equation number 2. Okay, and so these two equations, we are in the same variables, right? We have two variables and two equations. So in order for us to solve a system of equations, the number of equations should match the number of variables. So if we have two variables, x and y, we have to have at least two equations to solve for x and for y. And so, okay, how would we solve that? Right, our intuition will say that, well, let's go ahead and try to solve for one variable and then maybe plug in into the other variable. We can do that, right? So in the first equation, right, let's use first equation. So we're gonna have y to be equal to, so if we subtract 2x from both sides, we're gonna have 5 minus 2x. And then the second equation is still gonna remain the same. So 3x minus 2y is equal to, right? That's how it's gonna look like. Okay, so now let's go ahead and plug in first equation into the second equation. Okay, so we're going to have that. We still have y is equal to 5 minus 2x. But now in the second equation, we have 3x minus 2 times 5 minus 2x is equal to 4. All right. So, okay, now our second equation is in terms of x only, right? We no longer have a y. So this was the substitution method, right? We essentially substituted. We just got rid of one of the variables because we were able to express it in terms of the other. So now we can go ahead and actually solve the equation. Okay, and we know, so our final solution will have the x value and the y value, right? Or we also call it an order pair. So in the first equation still remains as y equal to 5 minus 2x. The second equation becomes 3x minus 10 plus 4x is equal to 4. Okay, so first equation, y equal to 5 minus 2x. Second equation, so let's move 10 to the right. So we're going to have 3x plus 4x, that's 7x, is equal to 14. So we know that what is x equal to? It's going to be equal to 2. Okay, now we can plug in into y. So y is equal to 5 minus 2 times 2, which is equal to 1. Okay, so our solution is, I'm going to say x equal to 2, y equal to 1. Or, in other words, we can write it as an order pair, so 2, 1. So 2, 1 is the point of intersection of the two lines that we have, right? This is where we're going to intersect. This is our solution to their intersection. All right, so there are multiple ways we can solve it. And I'm going to be referencing the book for the methods of solutions. And so we have the following. So let's take a look. So the method, we can have substitution, which we just took a look at. We can have a graphical way. So as Desmos, for example, you can graph the equations on Desmos, or you can graph it on the graphing paper and find intersection. You can do it via elimination and Gaussian elimination. So the last two we're going to be talking about later. Meanwhile, this is the 4 common ways of solving the system of linear equations. And after that, we will also be taking a look at the matrices. And we're going to define what a matrix is and why is it useful. Because matrices will allow us to solve a lot of problems. And in engineering and science, most of the equations, it's going to be more than 2 equations most of the time. So we need matrices to solve it. And we're going to learn properties of matrices as well. So, okay, but today we're going to be doing the first 3, essentially. So let's go ahead and take a look at the method of substitution and actually summarize how we have to approach it. So our step 1 would be to solve one of the equations for one variable in terms of the other, right? So we're going to have y equal to f of x, right? Some sort of f of x wherever we solve it, but we have to make sure that on the right-hand side, we do not have any y terms. Then we want to substitute the expression found in step 1 into the other equation, right? Because we have 2 equations, so we want to substitute y into another equation. So now the second equation will be only in terms of x. Then we want to solve the equation obtained in step 2, so essentially simplify and solve for x, right? So here in this case, solve for x. You can also do the same thing for y. You can reverse it. It doesn't matter. Whatever is easier algebraically to deal with. Then back substitute. So the value obtained in 3, we can substitute back into our equation right here. And once we do that, we were able to find y. And then we can also check the solution by plugging in the x value and the y value and making sure that the numbers do make sense. Okay, perfect. So let's take a look at another example. So let's go ahead and do this example. So example 2. So let's say we have x plus y is equal to 4 and x minus y is equal to 2. Okay, so once again, we have 2 equations. Let's go ahead and rewrite the first equation. So we're going to solve for y. We're going to have y is equal to, so what are we going to do? We're going to subtract from both sides. We can have, okay, y is equal to 4 minus x. And here we still have x minus y is equal to 2. Now, all right, so here, solve for y. Then, the next step, we're actually going to substitute. Okay, so we're going to have still y is equal to 4 minus x, right? And then this one, we're going to have x minus 4 minus x is equal to 2. Now, our next step is going to be solve for x. Okay, and that's going to be, so we have y is equal to 4 minus x. And here we're going to have 2x minus 4 is equal to 2. Okay, and now we're solving for x once again. So we're going to have 2x is equal to 6. So 2x is equal to 6. So that means x is equal to 3. And we still have y is equal to 4 minus x. So now plug x back in. And we will have y is equal to 4 minus 3, which is equal to 1. And x is equal to 3. So our order pair is going to be 3, 1. Okay? That's our solution to the system of the 2 equations. Right, perfect. And so now, let's actually take a look at some of the applicational formulas. And let's take a look at some actual applications. So let's go ahead and work on this problem. So in the previous few lessons, we were talking about the annuity and the interest rates. So let's actually take a look at this problem. So a total of $12,000 is invested into 2 funds paying 5% and 3% simple interest. The total annual interest is $500. How much is invested at each rate? Okay, so we know that we invested into 2 funds in total of $12,000. So I'm going to say that we have 2 funds, right? Fund number 1 is going to be X. Fund number 2 is going to be Y. So what do we know? We know that X plus Y is going to be equal to $12,000. Okay. What else we know? We know that the 2 funds paying 5% interest and 3% interest. Okay, so that means it's going to say, well, respectively, right? So for X is paying, let's say, R1, this is interest rate, it's going to be 5 over 100, which is equal to 0.05. And then Y is going to be the R2, which is 3 over 100. And that's going to be 0.03. Okay. So now our second equation, we told that after that interest, the total annual interest is $500. So that means 0.05 times x plus 0.03 times y must add up to $500, right? Because that's the yearly interest, the annual. Okay. So clearly we do have two equations here. Two equations, two unknowns. Okay. So now what we want to do is, well, the bottom equation, the second equation, isn't nice, right? We can still modify it, right? We can still modify it. As long as we do everything from one side to the other side, right? So what we can do, we can just go ahead and multiply it by 100. Let's do that. So the top equation is still going to be x plus y is equal to 12,000. But the second equation is going to be 5x plus 3y is equal to, so 100 times 500, this is 50,000. Okay, now we can solve this equation by substitution. All right, so let's do the substitution. So we're gonna say, okay, y is equal to what? It's equal to 12,000 minus x, and then we can plug in. So we're gonna have 5x plus 3 times 12,000 minus x, and that's equal to 50,000. Perfect. So now let's go ahead and solve for the x value. So here we have y is equal to 12,000 minus x, and here we're going to have 5x minus 3x, which is 2x, is equal to 50,000 minus 36,000. So 2x is equal to 14,000. Okay, so that means x is equal to 7,000. So $7,000 were invested in the fund number one, right? So how about y? Y is going to be 12,000 minus 7,000 is equal to 5,000. So y is equal to 5,000. And so 5,000 were invested in under 3% and 7,000 under 5%. So x is equal to 7,000. Okay, and essentially the system, or the corresponding point, is 7,000 comma 5,000. Right, that would be the solution to this system. Okay, perfect. So this is a very nice example. And of course, it's nice to have linear equations, but a lot of times we do not have linear equations. So when we are working with nonlinear equations, and that's going to be our next topic here. So we're going to talk about nonlinear equations. So nonlinear equations are the equations which are not line, right? We can have parabolas, we can have hyperbolas, we can have cubic polynomials, etc. So nonlinear equations is when we dealing with those kind of equations. But they become much more difficult because substitution will not work as a general method, because sometimes it's really hard to solve for the variable when you have a nonlinear equation. So a simple nonlinear equation where we can solve substitution is when one equation is nonlinear and the other equation is linear. Okay? So the first case, so example, call it 1, right? So this is example 4, or the second topic. So that is going to be equal to, so let's see, we're going to have something like 3x squared plus 4x minus y is equal to 7. And then 2x minus y is equal to -1. Right, so clearly the first equation is nonlinear because we have x squared. So the moment we have some sort of nonlinear, so bilinear operation is going to be addition, subtraction. This is linear, or constant multiplication. So the moment we have something more complicated, like a power or a logarithm or any kind of exponential, that becomes nonlinear. So x squared is considered nonlinear because you're multiplying x by itself. Okay, but the second equation is still linear. So what we can do, we can solve for y, right? So what are we going to have here? Y is equal to what? It's going to be 2x plus 1, right? That's going to be the equation for y. Meanwhile, the top equation still remains as 3x squared plus 4x minus y is equal to 7. So now let's go ahead and actually substitute. So we will have in the first equation 3x squared plus 4x minus 2x plus 1 is equal to 7. And y is equal to 2x plus 1. Okay, so in the first equation, what are we going to have here? We will have, let's go ahead and try to solve it. So we're going to have, if we simplify, so it's going to be 3x squared plus 2x minus 1 is equal to 7, so it's going to be minus 8. Okay, is equal to 0. So I think we can factor it out. So if we consider it the following way, we can have 3x squared plus 4 plus 8x. Right, so let's see. Will that be... We can do something like 6x minus 4x minus 8 is equal to 0. And so we're going to have, if we factor out, we're going to have 3x times x plus 2 minus 4 of x plus 2 is equal to 0. And we have 3x minus 4 times x plus 2 equal to 0. Perfect. So that's our first equation, and we have two solutions here. What are the solutions? So either 3x minus 4 equal to 0, or x plus 2 equal to 0. So that means x here is going to be 4/3, and x here is going to be -2. Okay, so once we solve for x, we have x1 and x2, so we're going to have two sets of points. Why? Because we had a nonlinear equation, specifically quadratic equation. Quadratic equations, most of the time, have two solutions. So of course, there might be special cases. But in this case, we got the two x values, so we're going to plug in both. So we're going to have y1 is going to be 2x1 plus 1, which is equal to 2 times 4/3 plus 1, which is going to be equal to 11/3. So our first solution is 4/3, 11/3. Okay, and our second solution, y2, is going to be 2 times x2 plus 1, which is equal to 2 times -2 plus 1. It's equal to -3. So our second solution, second point, is going to be -2, -3. All right, perfect. And sometimes, so the difficult part about nonlinear equations is that we might not always have a solution in a real sense, right? So let's take a look at one more problem. So example 2. So let's say we have something like -x plus y equals 4 and x squared plus y equals 3. Right, at first it seems, okay, well, not much different than the previous equation, right? But we can't immediately say if we do or do not have a solution to this. So first thing is, of course, let's go ahead and do the substitution. So let's solve for y. So y is going to be 4 plus x. And then substitute. So we're going to have x squared plus 4 plus x is equal to 3. So now in the second equation, let's go ahead and solve for x. So we're going to have y equal to 4 plus x. And on the second equation, it's going to be x squared plus x plus 1 is equal to 0. Okay. So if we use a quadratic equation for this, we're going to have that x1, 2 is equal to -1 plus or minus 1 minus 4 over 2, which is equal to -1 plus or minus square root of -3. Right, so discriminant here is negative. So that means no real solution. So, okay, and that sometimes might be a problem. So that means there's no real solution, so that's it, right? We cannot solve that system of equations. So that is the difficult part about nonlinear equations, is that even though it might seem that it's pretty easy to solve it at first, but then we run into issues of that the solution simply does not exist. Okay, and of course the nice part is if we can solve it graphically. right? If we have access to the tools, graphical solution might be more appealing to us than trying to solve it just numerically and analytically. So let's take a look at some of the graphical solutions. And essentially, we're just doing the graphs of the equations. So the first equation graph, the second equation graph, and let's take a look at where do they intersect. So here that would be an example, right? So all of the cases we've done so far. So we had first equation, second equation, so they were intersecting 2, 0, right? 2 lines intersecting, perfect. Now if we have a parabola and a straight line, so now we have 2 intersections, right? That's why we had 2 points. And here, as in the previous example, which we just did, right, which we just solved for, we tried to find solution, but that's how the 2 equations look like, right? They never intersect. They're never gonna intersect ever. So how would we modify this equation to have intersection points? Well, if x squared was negative, right here, if we add a negative sign, then that parabola would flip and we would actually have 2 solutions, right? But in this case, we have no real solutions and intersections. Okay, and sometimes we cannot just simply substitute and mathematically solve for the problems. So, and the example of such would be the following. So, example 3. So we might have something like x plus y equal to 1, and then y is equal to ln of x. Right, also 2 simple equations. One is a line, one is a logarithmic equation. But it's not clear how do we need to proceed with substitution because, well, we can substitute, right? Y equal to 1 minus x, right? So y equal to 1 minus x. But if we plug that in, it does not help us much, right? Because we have x on the left, x on the right, we have logarithm, we cannot quite simplify it. So the way we can do it is we need to think of how does the 2 equation look like. So sometimes graphical solutions will help us at least visualize for how many solutions we might be possibly looking, right? And so if we graph the 2 equations, we will find out that there's only one solution, right? And that solution is a simple solution. But so y is equal to ln of x. So what we can do, we can try to guess, right? So if let y be equal to 0, so then 0 equal to ln of x, and we do know how to solve that kind of equation. We're going to put both sides e to the left-hand side, e to the right-hand side power, so we're going to have 1 is equal to x. Okay, and then we can plug that in back to the equation, and we'll find out that y is equal to 1 minus x, which is equal to 1 minus 1, which is 0. So that checks out. So our solution point for that equation is 0, comma, it's 1, comma 0. So 1, comma, and that's going to be our solution to this nonlinear system of equations. And of course, it might get more and more complicated as the equations can get more complicated. So when that happens, computers are the ones who solve such equations. And that's why computer programming and modeling is so important for mathematics. All right. Now, let's take a look at the next part is, of course, besides having the substitution, we can also do elimination, right? So that's going to be our last part for today. We're going to take a look at how can we actually eliminate some of the variables. So we don't always have to substitute because substitution might be inconvenient for us to use. So let's take a look. Look at this example. So example 3. So if we have 3x plus 5y to be equal to 7, and then negative 3x minus 2y is equal to negative 1. So we have a system of 2 equations, right? Both of the equations have x and y. X is aligned under x, y is aligned under y, constant is aligned under constant. So what we can actually do, we can just sum up the 2 equations. But for us, it only makes sense to do that if and only if one of the variables is going to go away. So in this case, we can notice that 3x and negative 3x are actually going to go away if we add them together. So 3x minus 3x is going to be 0x. 5y minus 2y, that's going to be plus 3y, is equal to 7 plus negative 1, that's going to be 6. So we end up with the equation 3y equal to 6. So that means y is equal to 2. Perfect. And then what we can do, we can just simply substitute y being equal to 2. Let's go and substitute in the first equation. So we have 3x plus 5 times 2 is equal to 7. So 3x plus 10 is equal to 7. So that means 3x is equal to negative 3. So x is equal to negative 1. So our solution here is negative 1 comma 2. So as you can see, without doing any kind of substitutions, we were able to solve by using elimination, right? This is called method of elimination. So, or we can just say method of elimination. So we are eliminating one of the variables that we do not like. And or we want to just get rid of it because it's much easier to get rid of it. So sometimes we might be able to actually multiply equations and add constants to it, right? Multiply equations by the constants and then manipulate it. So method of elimination can work this way. So first we're going to obtain the coefficients for x and y that are different only by sign by multiplying all terms of one or both equations by suitably chosen constants, right? So essentially, if we had something like 2x plus y is equal to 1, and then x minus 3y is equal to 2, right? So in order for us to do that, well, let's go ahead and multiply the second equation by negative 2. So if we do that, the first equation remains the same, 2x plus y equal to 1, but the second equation becomes negative 2x plus 6y is equal to negative 4. Okay, then we can see that we have a positive 2 and a negative 2. So when we add them together, they're going to cancel out. So that's essentially what number 1 is about. Then we're going to be adding the two equations to eliminate one of the variables, right? So here, if we add the two equations, we're going to have 0x plus 7y is equal to negative 3. Okay, then solve the equation. So y, because this one becomes 0, is equal to negative 3 over 7. And then back substitute. So now we're going to use the value which we obtained, so the value of y, to substitute back into one of the equations, right? We can use any of the equations, either first one or second one. The rule of thumb is to use the equation that is the easiest to algebraically solve, right? So especially if you're struggling with algebra and you feel like it's hard for you sometimes to solve equations or dealing with fractions, choose the easiest equation that requires the less effort to plug into. So once we back substitute, we are able to solve for the other variable. So out of the two equations, or out of the two equations, original equations, I like more the first one, right? So we're going to have 2x minus 3 over 7 is equal to 1. So 2x is equal to, we're going to have 10 over 7. Okay, and so that means x is equal to 5 over 7. Perfect. And then we can plug it in and check that that's actually going to be the solution. So our solution for this equation is going to be 5 over 7 comma negative 3 over 7. That's going to be our solution. Okay, so now we can slightly faster solve the system of equations, because we are able to just eliminate the variables we do not like. And now let's take a look. Let's try to interpret the solutions to some of the equations. So here we go. So for a system of two linear equations in two variables, right, because that's what we've been working with, we have x and we have a y. Right, so the number of solutions is as following. So number of solutions, so exactly one solution, right? If we have one solution, just as we had the graph there, the two lines intersect at one point, and the slopes of the two lines are not equal. Okay, so if the slopes are equal, then that means the lines are parallel, which is not good for us, because with parallel lines, we either have no solutions or we have infinitely many solutions if the two lines are laid on top of each other. Then, as we said, the infinitely many solutions, the two lines are coincide, or essentially identical. They lay on top of each other, and that means the slope of the two lines are equal. And then NOR solutions, the two lines are parallel, and the slopes of these equations are equal as well, but they differ by a constant of addition. So that one is an interesting part. So let's take a look at this equation right here. So here, perfect example. So here, we have that first equation is negative 2x plus 4y is equal to 1. Second equation is x minus 2y is equal to 3. Let me actually adjust the second equation. We're going to have, if we multiply it by negative 2, I'm going to get negative 2x plus 4y is equal to, so I multiply by negative 2, so it's going to be negative 6. And our top equation is negative 2x plus 4y is equal to 1. So these two parts are identical, right? They are identical, but they are equal to different numbers. So what does that mean? No solution, right? Those lines are parallel. And of course, we can simplify and we can rewrite it in terms of y is equal to mx plus b, right? Y is equal to mx plus b, and you will clearly see that these two equations are indeed are parallel. So, and that's sometimes it's very easy to see, but sometimes it might be the tricky part, right? So next lesson, we're going to talk about the multivariable linear system and some of the Gaussian elimination. After that, we will move on to matrices. Right, see you next time.